At this point, we have for each movie I computed the Dij for all the j's out there. I've got a list of numbers. Let's arrange these in descending orders. Okay, these are the Dij values, and maybe movies 5, 8, 10, 2, and so on, with respect to movie, say I equal 1, the first movie. Okay. All right, very good. If you look at this and say, some of these are real big numbers, some of these are real small numbers, real negative numbers. Again, remember, this actually can be either a positive or a negative value. So we will say those that are very positive and those that are very negative are both useful, because they are very similar or very dissimilar movies. So let's just look at the absolute value of Dij's. And we want those that are big to be included. Okay, so we pick the top, say, 5 movies. Top either meaning they are really big here or really big here. Okay, and that will define what we call the neighborhood, a list of other movies with respect to this given movie I. So for example, L1 could be movies 5 and 8. Let's say there's a movie 21 down here, 21. Okay, now I say, who determines how big the set is? How long is the list? Who determines basically the cutoff threshold of the Dij value? Well, the one that will be determining this is you, okay, the recommender. So there are quite a few rules and guidelines in determining how big is this list. If you make it too big, then you are indeed incorporating the comparative information with respect to many other movies, but some of them are so weakly coupled with this movie that it doesn't quite matter. So just adding too much noise. On the other hand, if you include too few neighborhood movies, then you're not fully leveraging all the information, and then you are losing precious information about other movies. So that's not good either. We won't have time to go into the exact art of picking the right size, and that's indeed part of the reasons why it took many computation for these teams to compete in the Netflix prize. But roughly speaking, the idea is that if you like movies, say Schindler's List, and say Life is Beautiful Life, then maybe you like Dr. Zhivago. If you dislike E.T. or dislike Lion King, then maybe you also dislike, say, Toy Story. Okay. So that's the idea. The idea is that we're going to look at all these movies as points in the space. Those that are very close by this cosine theta metric, we'll call them neighbors. And therefore, for each movie I, we will define a neighborhood by the absolute value of these cosine coefficient values. So now that we have defined what is the metric cosine similarity, and from there we have defined what is a neighborhood for each movie, we can finally define the predictor based on that information, called the neighborhood predictor. So the neighborhood predictor will be denoted as R hat UI, but we have already used that symbol to represent the baseline predictor. Let's add a sup n. This n does not mean the number of users or movies. Is a shorthand for neighborhood. Okay, so we want to find out what is R hat sub UI sup n. This is basically the original baseline predictor, now plus what we learned from these neighbors. We learn from these neighbors that if a neighbor movie J in the shifted rating R2D, okay, again R2D is just R minus R hat, in this shifted space, depending on whether J is positively correlated with movie I or negative correlated with movie I. It's going to give us some information. So we want to add up those information, summing across all the movies J indexed by J in the set L sub I. So we have to weight each such rating by a neighbor movie J in some way. What should the weight be? One choice is just let weight be the cosine coefficient itself, Dij. Now, this may not be the best choice. We just don't have time to go into optimizing this particular choice of the weights. So let's say it's just Dij. So if Dij is positive, we're adding to the prediction. If it's negative, we're subtracting from that. And then we have to normalize somehow, right? Because we might be adding a lot of these movies in the neighborhood. So we have to divide that by the magnitude of the weights. The weights can be, it's just Dij absolute, summing over J in the neighborhood for movie I, Li. Now, why do we put absolute sign here but not here? Well, because in normalization, if you don't put absolute value, the positive and negative Dij's will cancel each other. So that's not the intention, to count their size. But in the numerator, if we add the absolute value, then we get confused whether J is very similar to I or very dissimilar to I. That's why when we calculate the influence by neighborhood movies J, we use the actual Dij, which could be positive or negative. But when we normalize by their size, we have to use the absolute value of Dij's. Now you can make it even simpler by just making the weights 1. You simply just count, add up the R2Ds and divide it by the size of the neighborhood. That's it. That turns out not to be performing very well. So we use a slightly more involved weights here. All right, so this is what we have been looking for in the last 80 minutes. This is the neighborhood predictor that will enable you to get quite far ahead in the Netflix prize competition. It composes of 2 parts. One part is the baseline predictor. Again, how do we get to the baseline predictor? Very simple, by solving the least square problems involving these BUs and BIs. Because the baseline predictor, R hat, is just the lazy average predictor plus BU plus BI for each UI pair. Okay, so solve least square based on the ground truth, train your parameters, U BI star BU star, stick it into the predictor, you get R hat. The second term in the neighborhood predictor is the actual neighborhood information. Again, we use the cosine coefficient as the metric. And then for each movie I, we define a neighborhood of a certain size. And then, based on that, we say all those movies J in that neighborhood set will be weighted with a certain weight, for example, the Dij themselves, and then normalized. This is the total influence in the prediction of UI.